Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will continue our discussion about analysis of variance, ANOVA. To be more specific, we will be talking about the ANOVA table. And what we're going to be doing in this video is trying to establish a relationship between a hypothesis test procedure that we have already discussed and the ANOVA table. Okay, let's begin. So I prepared a little example for you, okay? So the idea is that I'm going to be showing you kind of a toy example, a small data set with 12 observations. And the idea is that those observations represent sales, okay? And we also have the information about where those sales took place, okay? The countries where they took place. So there we are, our 12 observations, and again we have the information about where those sales took place, okay? 4 observations per country. Country A, country B, country C, right? And if you compute the average for each of those sales, by country, you're going to end up with an average of 8 for country A, an average of 10 for country B, and an average of 12 for country C. Okay? Okay. So, now also, on the next slide, what I did is I added up all these guys, all 12 sales, and then I divided by 12, and that gave me the average, and for all of them, right? So the average for all of them, ignoring country, is 10. Okay? Okay. So up to this point, we know we have 3 means for these 3 different countries, and we have also the average ignoring the information about country. Okay? Okay. So, on the next slide, what I'm trying to tell you is that if we wanted to predict the next sale, right, we could use this information to come up with a prediction. But we have 2 choices. One, the country where the next sale is going to take place is not known. We don't know where that is going to happen, or we do know where it's going to happen. And depending on that, right, we are going to have different choices for our prediction. So, if we don't have any additional information about the next sale, well, it makes sense. It's a reasonable idea to use the sample mean of those 12 observations, that is 10, as a prediction, right? Okay. So, and the thing is that it's a good idea, and we can show that it's a good idea because the sample mean is going to minimize the square distance between what we saw, what we observed, and what we predicted. Okay? And we're going to see that that makes sense, that agrees with our idea of least squares estimate. Okay, using a linear regression model, we're going to see that that intuition makes sense actually. Okay. Okay. Now that's situation number one. If the country where the sale is going to take place is not known, right? But if we know where the next sale is going to take place, then we could, provide two different predictions. One, we could use the sample mean, just like before, 10, or then depending on the country where the next sale will happen, then it would be, our prediction would be either 8, 10, or 12, depending on the country, right? So, but note that if we do that, right, if we use the mean for a particular country, then what we're doing, our prediction is ignoring the information from another 8 observations, right? So now that we have talked about our different choices as far as prediction goes, right, you will see that what we need is to come up with a procedure that is going to guide us in this decision process, right? And well, the way of deciding which prediction we should use is doing a hypothesis test in this case, okay? So again, going back to our example, right? What we're going to try and do is using a hypothesis test to see what's the better idea, using the sample mean using all 12 observations, or if we could just restrict our attention to the mean coming from the country in question. Okay? Okay. So let's talk about that null hypothesis for, well, the null and the alternative hypotheses for that hypothesis test. Okay. So our null hypothesis will be all those columns are the same. Okay. Well, the mean for those columns are the same. Against the alternative, the means for those, at least one of them differs, right? The mean for one of those countries is not the same. Okay? Okay. Now, let's talk about, let's go back to that situation number 1 and situation number 2, right? And see if we could write down a model for that kind of situation, right? So if we have that situation, right, and we want to use a linear model, let me call it model 1 for situation 1. Okay, so basically what we're saying is something like this. We have an observation y1, and then since we're saying that it doesn't matter which country they come from, right? We're not taking into account that information. We can use mu1 as a common mean, okay? all countries. So we would have something like this. We have 12 observations. So let me write down just a couple more. Note that, well, it is starting to look like one of our linear regression models, and that's the idea. So there we are, our 12 observations. We just want to use a constant, right, to predict these guys, right? We have an epsilon that represents a random fluctuation. And the assumption for the epsilons is the one we always have, right? That distribution of the epsilons is normal with mean 0 and some unknown variance, sigma squared. Okay. Now let's talk about situation number 2. So if we're going to be using a different mean depending on the country, basically what we're saying is this. Let me call it model 2 for situation 2. Okay. So for situation 2, what we're saying is, well, if you have something from the from country A, right, then you will have a mean. Let me call it mu1. Okay, but if you have an observation coming from country B, then you will have a different mean. And that applies for the next 4 observations. Make sense? Oh, let me change this. You guys agree? And finally, for the last country, country C, then what we're saying, since country matters, each country has that information, right, matters, then each country has its own mean. Okay? Makes sense, right? So we have these two competing models. And under the null hypothesis, right, what we're saying is, guess what? You know, all of them are the same. The mu, the population mean, right, for each of those columns is the same. If that was the case, if mu1 equals mu2 and that equals mu3, the second model clearly becomes model number 1. Can you see that? So since when the null hypothesis for this more complicated model is true, and that reduces to model 1, let me refer to this guy, to the simpler model, as the reduced model. And since this one is more complicated, it has more parameters, right? Let me refer to this guy as the complete model. Okay? Make sense? Okay, let's keep going. So let's talk about the again about the consequences of rejecting the null hypothesis. So if the null hypothesis is rejected, right, then as far as predictions go, right, we know that null hypotheses, all of them are the same. If we reject it, then that is telling us that the information about country is relevant, and then what we're going to be using is the average from sales that took place in the particular country that we're going to be predicting the next sale of. Okay? Okay. So that's the practical implication of rejecting the null hypothesis. Okay? And if we can't reject, if we fail to reject the null hypothesis, then we're going to be using just the plain average of those 12 observations. Okay? Okay. So, it turns out that an F statistic makes sense to carry out that hypothesis test. Okay, and well, at this point, when you see that, maybe you should start thinking, we have talked about F tests before. We have compared complete models or more complicated models against reduced models. So maybe something that we have done together is going to be applicable to this situation. Okay? And this is just describing the rejection region for this particular F test. Okay? And then let's try and see if we can make sense of this situation using our partial F test. Remember that we talked about that? Okay, so when we talked about partial F tests for nested models, we had this test statistic, which we know has an F distribution. Okay, so we'll see if we can apply that situation and see if that agrees with this idea of an ANOVA table. Okay? Or what's the relationship between the two, between the ANOVA table and our partial F test. Okay? So let's launch R and let us start doing some calculations. Okay? So first we need our data set. Okay. So going back, well, let me enter the information here, the data. There we are. So y happens to be 6, 10, 7, 9, 10, 8, 12, 10, 14, 13, 11, 10, right? Just to check. So mean of y, 10. Okay. Okay. So we have our data set there, right? Ignoring the information about country. Okay. Now, let's talk about these two models, the reduced and complete model. Okay. So for the complete model, basically we can write this down using matrix notation, like a vector y with 12 rows and 1 column, and our design matrix x will be a column of ones times a beta parameter, which is only one number, mu1, plus a vector of random fluctuations with 12 rows and 1 column, 1 epsilon vector. Okay, so as I said, our design matrix x in this case is just a column of ones. Okay, so let me call that single column x0, and what I want is I want to repeat the number 1 12 times. Okay. Okay, so now what we said here, right, is that if we are if that is the situation we are considering, we're going to ignore the information about country, then a good predictor will be the the average of those 12 observations, which is 10. We'll see if using a linear regression model like the one we're considering here, like model 1, we end up with that kind of answer. So let's fit that model. We said that this guy is the reduced model, so let me call it mod R. So we use the LM function. Again, we know that the syntax is first the response variable, and then our predictor, right? Now note that we don't have for this linear regression model an intercept. Okay, so let me just remove that guy. Okay, let's find the coefficient because it's just 1. Guess what? It's 10. It matches. So the sample mean in this case, it's the least squares estimator. Okay, so it matches with the intuition, right? Let's do something similar for the second model. Right now we want to see what happens if we make a prediction taking into account the information about country. Okay, so now let's talk about that complete model. Let me show you this again. Now what we have to do is again come up with a design matrix. So note that in this case we could rewrite it using matrix notation as a vector y of with 12 rows and 1 column, and the design matrix is going to look something like this: 1 1 1 1 and then 8 zeros. That's the first column, and then we're going to have 0 0 0 0 and then 4 ones, right? And finally the third column of our design matrix will be 8 zeros and then 4 ones. Okay, and our beta, our vector of beta parameters is going to be a 3x1 vector with mu1, mu2, and mu3 in it. Make sense? Okay, so let me use x1 for the first column of our second design matrix. I'm going to repeat the number 1 4 times, as I said. Then I'm going to repeat the number 0 8 times. Second one we said is going to be a vector with 4 zeros first, then 4 ones, and then 4 zeros again. And last one is going to be a vector with 8 zeros and then 4 ones. Okay, now let's fit the complete model again using our LM function. The response variable is the same. We want to use these predictors x1, x2, and x3. We don't want a y-intercept, right? We don't have a y-intercept here. Let's see if let's see what the least squares estimates of mu1, mu2, and mu3 are. Guess what? Again, it matches with what intuition would tell you, that it's just the mean, the sample mean, if you're just taking into account the countries for A. In that case, the sample mean only for countries sales taking place in country A is going to be 8, right? And so 8, 10, and 12 are the sample means for each country, right? And those are the least squares estimates. Okay, nice. So now we said we would like to see if we can use our F partial test to compare these two models, these two situations, to make a decision as to what kind of model we want to use for prediction. Okay, so here we go. We know that let me remind you what the test statistic looks like, right? It's just we have a reduction in the sum of squares error, right? For reduced and complete, we divide by the right number of parameters, and then in the denominator we have just the mean square error for the complete model, right? Okay, so let's try and do that. First, let's try and find the sum of squares error for the reduced model. So we already have, right, it's mod R. Yeah, okay. So remember that if you want the residuals, one way of finding them is just with this, the name of the model, res, as in residuals. Okay, that's going to give you the residuals. In this case we have 12 residuals. We want to square them, and then we want to add them up. Okay, so now let's do something, and let me show you what we end up with here. Okay, so 60. Okay, now let's do something similar for the complete model, and let's call it SSEC, right? The error sum of squares for the complete model. So the difference is going to be SSER minus SSEC, okay, right? And then now n is going to be the number of observations. It must be 12. Good, 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 good. So now we need k, right? And remember that k is the number of parameters in the complete model. So in this case, we have mu1, mu2, well, the number of beta parameters in our complete model. So we have mu1, mu2, and mu3, okay? So k equals 3 in this case. G represents the number of beta parameters in the reduced model. In this case, we only have mu1, right? A single mean. Okay. And now we can find that numerator. It's just going to be that difference. We compute it, right? SSER minus SSEC, right? And it's going to be divided by k minus g, the difference in the number of parameters, right? So k minus g. So in this case, it's going to be 2, right? That difference. The denominator is going to be the sum of squares for the complete model divided by n minus the number of beta parameters. And that's important, the number of beta parameters in your complete model. Before, right, when we talked about these models here, when we talked about nested models, we had k plus 1 because this one here, for that particular situation that we discussed back then, had beta 0, beta 1 up to beta k. So it had a total of k plus 1 beta parameters. But in our case here, the complete model has only 3. Okay? Okay. So we know now, let me call it f star, our test statistic is just going to be that numerator divided by that denominator. Okay? Okay. So now let's go back to what we had here. Remember that we saw something that we called the ANOVA table. Okay? So we're going to try and make sense out of that ANOVA table. So they say, instead of, well, the source of variation here on the first column of an ANOVA table, you have the explained, unexplained, and total. You will have the second column is the degrees of freedom, third column sum of squares, fourth column the mean sum of squares, and then finally an F. Okay, you're going to see that there's a very close relationship between that table and the test statistic we just computed here. Okay, here we go. Sum of squares total. Okay, so if you use no model, meaning just you use the sample mean for all 12 observations, and you're going to be using that for your prediction, right? That is going to be the sum of squares total. Let me show you something. SSE, for the reduced model, 60, right? So that what they call the SSE, well, SS total, the sum of squares total, is just in our case in terms of our partial f-test, the SSE of the reduced model. Okay? Now, if you're going to be taking into account, right, the information about country, for any of the 4 countries, the first ones, right, we would provide an 8 as our prediction. For the next 4, 10. For the next 4, 12, right? Okay. And if you compute the difference between observation and prediction, and then you square those differences, you end up with 28. Let me show you something. SSEC 28. So what they call the sum of squares unexplained, right, is SSE, the sum of squares for the error for the complete model. Okay? So, the difference between the sum of squares of reduced and complete is 32. Okay? That's what these guys call the sum of squares explained, or the sum of squares for the treatment. That's what we would call before the sum of squares of the regression. Right? Okay. So now let's see what we have here, right? Do you see that too? Well, k minus g happens to be 2. Now, remember that we used in the denominator, right? N minus k, 9. Okay? So, basically, and see that, let me show you again f star, what we ended up with here. Okay? Let me show you the numerator. Denominator. Now it should make sense, right? The ANOVA table is just a way of finding your test statistic for a partial f-test, right? So the idea is here in the degrees of freedom for the total, right? In general, you're going to have n minus 1. So we have 12 observations, then total 11, right? Unexplained, n minus c, explained c minus 1, right? Okay. So what we have here is the degrees of freedom for the denominator, right, clearly, and the degrees of freedom for the numerator, okay? And you are always going to have 1 minus the number of treatments, or in this case it would be the number of columns, right? For this one, you're going to have, again, n minus the number of beta parameters in the complete model, right? This one here, right, is the sum of squares for the, as we saw, right? This one here, right, the sum of squares for the reduced model is this, right? You can find the one for the complete model, and then this one is just going to be the difference, right? Which is exactly what we have here in our test statistic, right? So what I want you to see is once you have these quantities here, it's game over. Why? Because this is how you do this, right? Once you have these guys. So 28 divided by 9 gives you this. 32 divided by 2 gives you this. And then your test statistic is just 16 divided by 3.111, and that's your F star. Okay? So again, bottom line, what I wanted you to see is that an ANOVA table is just a table that is going to help you compute the test statistic for a partial F test. Okay? Okay. Now, let's talk about the conclusion of this hypothesis test. So we can use the p-value approach, we can use the rejection region approach. Okay, the rejection region here in this case we're saying, well, if alpha was 0.05, all you have to do is find a critical value for an F distribution with the right number of degrees of freedom, 2 in the numerator, 9 in the denominator. Okay, so you know that you can do that easily. Just you have to find a quantile of an F distribution, and to do that you use the function QF. Since alpha is 0.05, you want to have 0.95 to the left of that quantile. You have 2 degrees of freedom in the numerator, 9 degrees of freedom in the denominator, right? So if your F star lies to the right of that critical value, you reject H naught. Okay, so that was the case, right? Ours was 5 point something, so clearly falls in the rejection region. So since it's greater, we reject H naught. What that means is that the information about country is relevant, and if you're going to make a prediction, you're better off using that information, right? Okay. Now, finally, let me show you a way of doing this, an ANOVA, this kind of analysis of variance, right, using R. Okay. Let's just copy paste this. So these are the first 4 observations, the ones that come from country A, then the next 4 from country B, last 4 from country C. We paste them together using that C function, right? So we're going to have sales. That vector is going to be 12 by 1. Then country, I'm going to be using a 1 to let R know that that's first country, 2 for the second one, 3 for the third one. Okay? And then the syntax is, first you need your response variable, the one that you want to predict, sales in this case, and then your predictor variable, country. And we need this additional parameter. Remember that in a regression model, right, we assume that the variance is the same, right? So what we're saying here is that the variance is the same for all these groups. So let's see, let's copy paste. Hopefully this works well. So see, what we have is that F star 5.14 degrees of freedom in the numerator, 2 degrees of freedom in the denominator, 9, and this gives you the p-value, not the rejection region approach, right? But we know that if you're going to be using the p-value approach, just compare the p-value against your significance level. If alpha, the significance level, were 5%, the p-value is less than 5%, then we reject H naught. So same conclusion as before. So finally, just a reminder about the assumptions, right? Since we're assuming that the errors are normal, that has distributional implications for the y's, so the y's are normal as well. We're assuming that we have a common variance, sigma, square, right? Which means that the standard deviations are the same for all those errors, right? And the independence between the errors, right, also yields results in independence, assuming independence between the observations, between the yi's. Okay, so bottom line, let me summarize what we learned today. What we learned today is that this ANOVA table, right, is just kind of tabular format that is going to help you compute a partial F test, okay, for this particular situation where you want to compare the means of C groups, okay? And once you have found the first two columns of an ANOVA table, then it's easy to come up with that F star, that test statistic, okay? And that's why people liked these tables in the past. But you know, the way that we can think about it, given what we have done together, is that, you know, what you have to do is just finding the sum of squares for the reduced and sum of squares for the complete model, right? Once you have those, the sum of squares for the reduced, which is going to be, you know, always the bigger or equal to this, right, is the one that we have as the sum of squares total in the ANOVA table. Then the sum of squares for the complete is the one that you're going to have in the explained or the treatments, okay, part. Then to find the sum of squares unexplained, or what we called before the sum of squares of the error, is just the difference between these guys. And once you have that, you're done, because here in this case it's always going to be the number of, in this case, countries minus 1 for the degrees of freedom, this one number of observations minus number of beta parameters in the complete model, right? So, and then all you have to do, because this is the goal, finding this guy, is sum of squares divided by degrees of freedom, sum of squares divided by degrees of freedom, and then once you have those mean squares, you find the ratio between those mean squares, and that's your F star. Okay? Well, that's it for now. Thank you so much for watching. Please keep working hard and take care. See you next time. Bye.